we have the visualization, we have the occupied stall numbers for this frame, the empty stall numbers as a readable number, an actionable number to think about logistics. And you also can have a CSV of those JSON detections if you were running with batch processing. Today, we're going to build a rapid model to identify empty and occupied stalls. How are we going to do that? Let's take a look at the video. So this is a drone footage of a parking lot, and I want to identify which stalls are empty and which ones are occupied. Before diving into computer vision and how we're going to do that, let's think a little bit and architect a solution. So, problem we're trying to solve is detecting empty versus occupied stalls and know which one are which. We need to think about what differentiates empty versus occupied stalls for our vision, right? So empty stalls don't have trailers, occupied stalls have trailers. So we could easily go and see that image and say that like stall number 645 is empty and all the other ones are occupied, right? Because 645 has no trailer on it. All the other ones had trailers parked. And how do we translate that thinking into logic? Okay. So not everything in the image is a stall. The stalls are the spots in the image that have numbers identifying it. So we want to look at the stall number, and the thing that we came to the conclusion that identified a empty or occupied stall is having a trailer, right? So we need to identify trailers. We need to identify the numbers and answer this question. Is there a trailer next, or at least to the left of the stall number? If so, that stall is occupied. If not, that stall is empty. And to actually identify the stalls, we can try to identify that stall number here, rotate it, put it through a OCR model, a text recognition model, and actually read that as 644, for example. So that's our mental model of how we're going to solve that particular problem. So, okay, step one, we're going to Rapid. We upload our video, right? So here's our video. And we prompt by what we're looking for. So we're looking for trailers and stall numbers, or let me put it in singular, trailer and stall number. So that's immediately what I get. If I move my sensitivity over here, I can see that the model picks up stall numbers. It's a little bit harder for it, but it does a pretty decent job on doing so. If I move to a different frame, I can also check that results are pretty good. So I have stall number positions, I have trailer positions. All right, I can run this in the entire video. And while it processes, it's actually running the detections on every frame. So we can see the magic happening here. It's very interesting to see that happening in all frames of the video. I can hit publish and use model, and voila, I have my API. From there, how do I add intelligence and logic to my computer vision solution? So I can click here in Open Roboflow Workflows. This is going to open the newly created workflow that Roboflow has built for me to find trailers and stall numbers, right? So this is how it looks like. I have an input here that inputs an image, but it could be a frame. This runs on video. I have a SIM3 model that detects stall number and trailer. I have a simple bounding box visualization, and I have my outputs, and I have two other blocks that don't matter right now, but this is how it looks like. If we test this workflow with that same photo, we're gonna see that the first run is gonna take some time, because it's the first time this workflow is running in our servers. But we're gonna be able to see that we do get predictions here, and there's a visual, and that visual is identifying the trailers. All right, because like we showed in the beginning, we needed to play a little bit with thresholds to see that stall numbers, and that's exactly what we're gonna do. I've lowered the threshold to 0.3, and we can see how it's gonna perform. And ultimate result is we get stall detections, stall number detections, and trailers here. All right, we're at the same step that we finished earlier. So now we can actually add intelligence and logic to that. So in order to do that, let's revisit what is our thinking process. So we have trailer positions, we have number positions. We need to verify that there's a trailer next to a number. And if so, it's occupied. If not, it's an empty stall. And as for the number, we can rotate. We need to crop that image, rotate it, and send it to an OCR model, and hopefully get a correct reading. And from that, we should have occupied and empty stalls through a computer vision pipeline. All right. And we're not going to build that workflow. I have it over here. It's actually a quite big workflow. And as you can see, it successfully identifies occupied and empty stalls. And if we go here to the JSON predictions, we got a pretty beautiful list of empty stalls as a text, not an image, and occupied stalls. So that could be used in logistics to watch this parking lot percentage of occupied spots, for example, and actually the precise location of the occupied spots. That's pretty good. And okay, let's go over on how we do that. I'm gonna use a second explaining workflow here that I've set up by duplicating the first one. And what we're gonna see is we're gonna go through each step and change those visualizations over here so we can see what's actually going on. So right now we're running our rapid model to find stall numbers, trailers. I got the threshold configured over here, and we have a bounding box and a label visualization. When we test this workflow, without all the logic over here, without all the blocks, just plugging it into the rapid model, which is a Sense3 model, we can open this image and see that it's identified the trailers and the stall numbers. That's great. That's step one. So here's how we're gonna do to verify if the stalls are next to a trailer. We're gonna add a horizontal padding to our detections. So for each bounding box, we're adding 400 pixels in the x-axis. So just apply a padding to those detections, and you don't need to believe me, we're gonna actually see that. Let me put this over here to the horizontally padded, also this to the horizontally padded predictions, and we should be able to see a different image over here and see how that detections transformation block actually works, right? Here it is. So these are our padded detections, right? So this is a very hacky way to find whether two objects are near each other horizontally or vertically, for example. So we added a good amount of padding to our detections. So now they're overlapping, which is great because if I have a stall number that overlaps with a trailer, it means it's an occupied one. If I have a stall number that does not overlap with a trailer, it means it's an empty stall. So that's our core logic. If there's overlap, it's occupied. If there's not overlap, it's empty. All right. So what we do then is we get those horizontally padded detections and we apply overlap filter. The overlap filter will use the trailer class as a filtering overlap class to keep only the detections that have some kind of overlap with trailers, meaning that we're able to actually visually filter the occupied stalls because they're just overlapping with our trailers detection. So let me change our visualization so we can actually see that happening in the image. But that's a pretty neat block here because you can play around with box being overlapping, either overlapping the center, overlapping any part of it, and actually filter detections based on that. So this is actually a pretty useful block. So if we go to the image, we can see that we don't have the trailer detections anymore. They were used to filter out which detections would be kept. And we don't have the empty stall one. So we actually know which stalls are occupied. And that's great. So we need to revert that horizontal padding, right? This was just a hack. So we could actually make the boxes overlap. So we can just revert that 400 pixels padding and rename those detections to occupied stalls. So this is what I'm going to show. I'm going to change our visualization to the rename to occupied stall block. And we can test our workflow. So this is the basic process to verify if those stalls were occupied, right? Let's wait to see what our visuals give us. And voila, we have our occupied stalls with the boxes not padded, like the original boxes. Yeah, and we also renamed the classes to occupied stall, right? With actually the same block, right? Detections transformation is a very powerful block. So how do we know which stalls are empty, right? Because we were able to use the overlap filter to get the occupied ones. How do we get the empty one? There's no trailer in there, right? One way to do that is we get the rapid model predictions. We filter only by stall number predictions, meaning we just throw away the trailer detections. We don't need them anymore. So now we have all the stall numbers, right? All the stall numbers here, and we have all the occupied stall numbers, which means that the difference between those predictions is going to be the empty stalls, right? We have all the occupied stalls and all stalls. So the difference between them is going to be the empty stalls. So what we could do is bringing those detections together in a detection consensus block. So what does this block do? It actually merges predictions with a predefined logic, right? So it gets predictions from many different models. Here I'm using 2 models, but you could put more. And it gets into a consensus of which predictions to actually display based on the rules we put here. So there's a precedence order here. The first models you add are priority on deciding that their prediction is staying. And you can configure the required votes, meaning how many predictions should show up in the same place for we to decide that it was a real detection, right? But in our case, we're using 1. And this is the trick here. You need to make it not class aware, meaning that if you had 2 boxes in the same place but with different classes, it's gonna pick one of them. It's not gonna filter by only comparing the same classes because we don't have the same classes overall. In here, we rename it to empty stalls, and in here, we rename it to occupied stalls, right? So we have 2 different classes, and we want to remove overlapping from those boxes. We're gonna use the detection consensus, and you don't have to believe me. We're gonna just look at it. I'm gonna move our visualization blocks and run our test again to see what's coming out of the detection consensus, right? So this is our basically our trick to merge those two predictions together again and not keeping duplicate boxes where there should be only one, right? So if we open our image, we're going to see that we have occupied stalls for all stalls that had the overlap and an empty stall for the box that didn't have the overlap. And we don't have extra predictions in here. And it's beautiful. We just solved our problem. Now, what's left? We actually need to read the stall number, right? So here's what we should do. We're gonna break those detections into two branches, right? We're gonna get the occupied stalls and the empty stalls, and we're gonna crop every occupied stall detection, meaning doing exactly this. We're gonna crop this tiny box here, right? So this is what this dynamic crop block does. It crops based on the detections. So we have here all the occupied stalls images, and in here all the empty stalls images. So we're gonna apply some pre-processing. So we're contrast stretching here to make the differences between the text and the background clearer. So we have a better difference at contrast, therefore improving the performance of our text recognition model, right? So it's just a trick to improve model performance. And we also need to rotate them, right? Because they're rotated 90 degrees to the left, and we need to rotate them minus 90 degrees to have them in the right position to be read by the OCR model. And for OCR, we could use anything here. We have easy OCR. We have a bunch of stuff. Here, I'm using OpenAI, right? OpenAI with GPT-5 Nano. Image detail, I'm keeping on high because this means we're sending a high quality image to OpenAI. And the neat thing about this is that you can use Roboflow managed API key here. So that means you don't have to go in OpenAI and create your account and do a bunch of stuff. Just to paste an API key here. You can do that. But if you want to, we can use our own API key, and then bill you for whatever usage you had here. So yeah, this is gonna read every image and try to detect which text is present in the stall. And it should give us a list of occupied stalls and a list of empty stalls together with the detection consensus kind of thing. So if we connect here in the output the occupied stalls, and that's a occupied stalls output, and we add another parameter called empty stalls, and that's the output of our OCR model. We should see running with our image, and this is gonna take a little while again because we're doing external API calls here, right? So our servers are actually talking with OpenAI. If we had 8 or 10 detections of stall numbers, we're doing that 8 or 10 times. So if we look at the JSON, we have the visualization, we have the occupied stall numbers for this frame, the empty stall numbers as a readable number, an actionable number. To think about logistics, we actually know the number of the stalls. We don't need to look at it, but if we want to look at it, we have the visual. And you can actually run this preview and into a video. I'm not gonna do that. It's a lot of external API calls together with some tree, which is a kind of a heavy model, but I ran it before, and here it is. This is our final result, all right? So if you really wanted to see that process into a video, this is how it would look like. And you also can have a CSV of those JSON detections if you were running with batch processing. And that's it. We reach our final workflow, which is this. And you can also plug in a byte tracker and detection stabilizer block if you're processing video. We're not going to do that, but this is our final workflow. And it looks like the exact same output we got here. And that's it for me.